By the way, feel free to ask questions from you guys. So I have some questions just to start things, but if you have any questions you want to ask the panelists around the big subject of Exascale, if you want to provide your own opinion, if you want to fight with the panelists, everything is fine. Everything is okay. And I'm sure that Addison also have his own questions, so he probably can also serve as a moderator and a panelist together.
I brought a stack of surveys with me.
Right. Let's kick it. And typically the first question that I always start in the last 5 times, which has become boring, is how do you define Exascale? So I'm going to skip that question, how do you define Exascale? I'm going to ask you the first question is, do we actually need Exascale?
Yes.
Can you explain your answer?
Yes. All right, so sticking with traditional high-performance computing for just a second, I mean, what I was saying earlier in my hyperscale talk is one thing they had in common was that high-performance computing applications can be done at an arbitrary level of complexity, that there's always a harder problem to solve. There's a lot of science that's still left, and I don't think we're going to get to the end of science anytime soon. There are always more complicated problems to solve. Models can be run at higher degrees of realism, more degrees of freedom. If you're trying to model a climate, down to the level of a tree, or you're trying to model a tsunami down to the level of how many jellyfish are getting caught up in it, these things are complicated, and there are always these worthwhile pieces of learning. One of the more fascinating conversations I had on the end user side, though, that had to do with Exascale came from someone on the finance side, since we were talking about finance earlier, trying to get a sense of moving finance through another power of 1,000 increase in scalability. And the guy I was talking to went immediately to risk management, which as much as people talk about high frequency trading, risk management is the larger, faster growing, more interesting, and more highly regulated part of the market right now, where everyone's trying to catch up. The best of breed in banking right now is to resolve your risk positions overnight. So if you've got investment managers, portfolio managers, traders, people who have tranches of credit cards, whatever they are that you're evaluating the risk of. Let's say it's a portfolio manager. You've assigned him or her a risk position, and you know that they're in compliance with their risk position at 8 in the morning, and all day long they go do whatever they want as long as they get back by 4 o'clock. And when they get back by 4 o'clock, you don't even know if that's where you want them to be anymore, right? Because the market's moved. And so to go from where they are today, where the best of breed is to go overnight, to say, can we get to some kind of intraday risk management, risk position checking? Can we go from there to more or less real-time risk management within some error bar that lets people move? And then can we go from there to real-time risk checking in response to changing market conditions that are resolving my risk position on the fly? Every one of those problems is 100 times more complicated than the one they're on today. There's a good case for Utilization, right, in finance that they would like to invest in. It's just complicated. And they'll get there as fast as they can. The hardware is part of it. You got to have the algorithms to do it. Do we need it? Do you want your money to be safer? Yeah, I think there's a good case for that, and that's just in the finance side. I think any industry you look at, if you double click at it enough, there's plenty of use cases for going to Exascale.
I see 3, at least from the scientific perspective, 3 big use cases that I think could benefit a great deal from as much computing as you can throw at them. One, as Addison said, would be climate simulation. The finer grain meshes we can use, the more we can predict the outcomes of the problem that we're in the process of creating for ourselves, and seem utterly incapable of steering our Titanic away from that iceberg. And the closer we get to it, the harder it's going to be to figure out what we need to do to get ourselves a habitable planet back. Another one is simulation of the human body. Brain, heart simulations, various organ simulations. There's a lot of research that is on the cusp of being able to be done, but we can't make forward progress without being able to increase the amount of computation that we can throw at these problems. The talk earlier on simulating the heart was a perfect example, but that's just one of hundreds with the human body. Things that we could be simulating to advance healthcare from where it is. And the third one that is particularly of interest to me, not that I'm at Lawrence Livermore, but we always get confused for being Lawrence Livermore, so it's a little bit close to my heart. And that is simulation of the nuclear stockpile. The global political climate right now is, to say it's complicated would be an understatement, but there are
it's scary is what it is.
Yeah. There are dangers today that haven't existed in this way since the Cold War, and it's scary the kinds of problems that we could be facing in the very near future. So getting a hold of our nuclear stockpile and keeping it not just safe, but prepared for whatever lies ahead is more critical today than it's been in a very long time.
I agree with all three of those, but I'd like to quickly piggyback on the brain one, right, if I can, because this is one that's really exciting to me right now, projects like Blue Brain. If you think back, to forever ago in the year 2000 when they mapped the genome, that's the kind of achievement that sounds like the end of a problem. We solved it, we've done it, we've mapped the genome. And the reality is that's the beginning of a whole new field of research that we call genomics, right? And you look at the arc of how that's gone over the last 16 years. We are getting close to having the same kind of moment where you have a comprehensive map of the human brain. And think about what kind of research that's going to enable, where you can now simulate or model traumatic brain injury or the neuropathy of conditions from autism to Alzheimer's, is a real game changer. That is going to take off like crazy when it happens, and it's not far away, and Exascale is right in there.
And I think the traditional, some of the applications also like earthquake analysis, prediction, tsunami analysis, and now we have this Zika virus coming. We will see again the next round of things. When the bird flu came a few years back, there was so much computing needed, and right. I'm sure here it will continue to rise. So these kind of like natural disasters, again, there are people have been working on, but the finer or better models are coming. I mean, that will require bigger and faster systems.
So what I'd add to that is sort of more of a historical perspective than one that's looking forward, which is the historical perspective is that we've been building for some time towards exascale. I mean, this is a thing that has been put in motion by many of the people in this room, and I'm certainly grateful for that, and I know many scientists out there that I serve at the Leadership Computing Facility at Argonne feel that way. We also have seen in the last 10 to 15 years moving from a space where a handful of scientists use significant high-performance computing resources to the point at which you cannot be a scientist or an engineer without touching some form of high-performance computing research or computational science. So the market has increased in size in terms of everybody who's involved with it on the academic side. At least the 20 years experience I've had in high-performance computing and computational science in 2 universities and 1 national lab has proved that to be true. We also know that we can build it, which we didn't know maybe 10 years ago. And I think you saw in some of the talks that people alluded to things like, yeah, it's going to run and we can build it, and it's not going to break every 35 seconds. So, you know, the vendors, I think, are well positioned to build such a machine. So all the pieces are in place, and it just so happens that, at least for the national labs, and I'm certain that there are other organizations out there, but I'm less aware of them, are in the process of gathering from the science communities, people that are in this room right now, and other places, you know, why we're building this machine. And so your voices, if you're a user in this room, how many people are users? Good, all right. Thank you for being here. I know it's late, but that's why we're here. So now we're looking at the users to tell us what are the most challenging problems they have to solve. Now that we've had all of this history behind us, now that you have all walked a long path with many people involved in the industry. So I'm here in as much to listen to you more than anything about what it is you want to do next, because we believe we can do it.
Dr. Panda's comment reminded me of another good example that's worth mentioning. I think it was Dr. C. Everett Koop who said it. The single greatest threat to man's continued dominance on the planet is the virus. There is a project going on right now at Berkeley Lab trying to model and create a single vaccine for the influenza virus that would work for all current and future strains. Right now, as you know, we have to get a new flu vaccine each year, and they have to try to predict what strains are going to come up and how to vaccinate against those, and it's an ongoing battle, and our scientists are trying to create the ultimate end-all and be-all influenza vaccine. But in general, the ability to simulate viruses and the effects of viruses on the human body and the effects of potential vaccines on those viruses could very literally spell the difference between the survival and the extinction of the human race as viruses and bacteria too, for that matter, become increasingly better adapted to beat us and harder for us to fight.
Yeah, I think another case is something that Baidu already discussed, and Brian Catanzaro from Baidu is going to be here tomorrow and probably going to mention it, that for doing what they want to do, they need a system in the scale of several exaflops today. So, you know, for doing machine learning or artificial intelligence, that's another case. So there is definitely a need for that. Now, any question from the audience? Yeah, go ahead.
Well, it's also going to be, you know, I understand the mapping of viruses that we have out now, but you have to realize part of our genome includes some of these viruses, some which do not affect us, and you have to map out. So there's been a project at Columbia, one of my professors down there is working on a viral project to map just what's in our body, bacteria, what's in our body virus-wise that we don't know about. You know what to do it.
Yes.
Part of your genetics has certain viruses in it that don't express the phenotype. So it's a matter of what's out there and mutates, it's a matter of what you have. Could you you actually create something why that virus isn't killing itself. It's not so simple as a cut and paste.
Right.
Okay.
Yeah, and I think in the same line, the entire field of personalized medicine, what people are talking, I mean, it's in a very early stage. I mean, to really to make it practical up to certain extent, I mean, we'll need significant amount of computing power. It will be again multiple exascale systems.
Was it? Yes.
I have a question on the, you know that Exascale will be here very soon. No, next day. Thing is,
It'll be here.
The Department of Energy has a lot of money. Anyway, question is,
Tell that to the Republicans. Just saying.
because Exascale is going to produce a lot of output. So where is the storage heading? You know, are we ready for storage? Input on output. Storage.
Yeah, in fact, I think if some people will see, I mean, the storage is actually, putting exabytes is much more easier than real exaflop performance. I mean, so I think the storage, pure capacity wise, but then how you really access that through the exaflop system, that is the big challenge kind of thing. So we may see early stage like exabytes of data will always be there available, and then the exaflop systems will come and then try to work together with it.
Yeah.
If you're talking about exabyte storage infrastructures, there's a good argument that they were there already. I mean, there are people who have, I think, exabytes of archive, or if you look at distributed networks over the internet like hyperscale, there's certainly an argument of networks of exabytes of information that are available. But in the conventional supercomputing sense, yeah, I've spent years talking about parallel file systems and the necessity of parallel file systems in greater scalability. We've seen Lustre really pervade a lot of the national lab market, although there's been considerable investment also in GPFS. But they really have not cracked the commercial side to a significant degree yet. The largest oil and gas companies, sure, have Lustre or other parallel file systems like PanFS installed. I'm starting to wonder whether or not I was wrong, and that we're not going to see a widespread deployment of parallel file systems in commercial markets, but rather that they'll catch the next wave, skip parallel file systems and move to object storage. We're seeing a lot of momentum around object storage now, and there's a good argument for why a file system free object store is a better model for a lot of exascale types of deployments.
I think in terms of sheer ability to store data, we can record and store an almost infinite amount of information already. Groups like the Long Now Project are working on ways of microscopically archiving massive amounts of data in ways that will last for tens of thousands or millions of years. But the tricky part is movement of data to where the computation resides, and then the speed of being able to act on that data. And in order to make those things happen at exascale, the key is really going to be how much of the computation can we move to the data storage. Getting information from place to place is one of the slowest and most expensive operations in an HPC system. And so the closer we can get computation to where the data already is, and the less we have to move it around, the faster we can make the overall system perform. And so a lot of the advancements, in my opinion, that are going to be coming in terms of storage aren't necessarily going to be increases in capacity, but rather increases in resiliency and increases in computational capability of the storage, like being able to perform certain encryption or compression type of algorithms, or arithmetic algorithms on the storage itself, so that pre-processing and things like that can happen a lot closer to the data, and by the time it gets to the CPU, it's in a format that's ready to be immediately digested by the more complex code.
Yeah, so another sort of spin on data movement is also something we're really, I think all the labs are heavily investing in, which is moving from data collected from the experiment into storage and modeling and analytics. And so, for instance, we're doing a lot of stuff where we're working with the advanced photon source and thinking about like pulling data directly off the advanced photon source and running it on a petascale machine like Mira, looking at it, cutting it up, doing analytics off of that. And so I think we're going to see more and more of that. And as we peer down the line into the experiment, we start to think about what can happen at the experiment in terms of capturing the data, right? So if I remember correctly, and if somebody knows this better than I do, please correct me. But I feel like the LHC only keeps like 1% of its real data, right? It kind of dumps the rest of it on the floor. And it won't as soon as the storage and capabilities catch up in terms of that instrument, as all instruments are that way. But being able to go all the way to right up to where we're sensing something and being able to do operations on that data to make it so that we can keep it for a long time. If you think about the next piece, which is you were talking about the long now, being able to store that data, that's actually my bigger concern, I think, which is where are you going to put your data for the near term, not the long term, which I think we can probably solve that problem, but where can you put your data in the near term? So you've computed on a major national resource on a machine that has an exabyte of disk storage, right? And we've seen people be able to do that right out of the gates, but then where do you put it next, and how do you keep it? And so I think that's an open problem that'll be interesting for researchers to work through in terms of how they manage data.
You mean visualization?
I mean, like going back and being able to do more research meta-analysis on that data. I mean, I think that's kind of a really important thing right now. You spend a lot of time generating that data. You could regenerate it. That's one thing. But maybe it's an event, right? And you can't regenerate the event off the experiment, but you want to continue to look at like all those events and see if you can find some more meaning or discover something new in that pile of data.
Yes.
So what are some of the industry's key challenges where a public-private partnership will play a role?
Sorry, the question is where can public-private partnership play a role in terms of unlocking these challenges? Software. Software is the number one challenge here. People will talk about power consumption. Power consumption is the hardest of the hardware challenges. So the software problem is harder. Assuming by exascale what you mean is a system that can run an application at that level of scale. If there's no requirement to run an application, then forget it. Okay, that's easier.
Not LinPack.
Even LinPack is hard, but then getting other applications to run at that level of scale. So the question is, what is the right model for public-private partnership in that sense, and which government should and would pay for it? Furthermore, is it more appropriate to give the money to an open source community to try to develop programming models, applications that'll scale to that level, which I think is the preferred bias of both the US and European governments, the Chinese government for that matter? Or is it more appropriate to invest that money with companies that already have software tools that compete in that space to try to help them to develop that further? I was talking to someone earlier today that it kind of gets in my craw a little bit when you see public money getting spent to develop software that will take business away from something that already competes in the market. But that's a personal opinion. I do get that there's a preference for open source out there. But I think software, in short, I think software is the biggest area for public-private partnership. I think the more difficult question is, what should that look like?
Even beyond Exascale?
The question was beyond Exascale. Exascale is an arbitrary milepost on the road. It is a problem today. It will be a bigger problem by the time we get to Exascale. It will continue to be a big problem beyond Exascale. I think we need public-private partnerships for greater software scalability in general, and that problem gets tougher as we go towards and beyond Exascale.
Yeah, I think some of these efforts are already taking place, like especially the labs like Livermore. A lot of vendors are coming together to contribute some components so that we can have a test bed, different people can have access. So it is already going on up to a certain extent, because every time a new level of machine comes, no single organization can just put it for experimentation. So it has to be a partnerships across different organizations.
And just for software or across the board?
This is for the entire thing. I think for the software, it's understanding the deployment, looking at the network level stuff. It is a continuum. Might be one of you can give some more details.
All of the major Department of Energy computational centers are invested in working with industry, both in software and in hardware, to advance the problem of exascale. And DOE has kind of taken the approach that we don't know which company or combination of companies has what's going to ultimately be the best solution. And so you'll see a variety of systems and investments that we're making in terms of pursuing a number of different technologies which ultimately will get us to exascale. You've got the Coral system at Oak Ridge and Livermore and Argonne. You've got the Trinity system at Los Alamos and the follow-on to that, which is going to be coming next. You've got the Cori system at NERSC. All of these different systems are taking different combinations of technologies and forming different partnerships with industry on both the hardware front and on the software front. For example, NERSC, and we heard earlier about Livermore, they're doing the non-recurring engineering partnerships which allow for user services personnel at NERSC to work with engineers at Intel and at Cray and at NVIDIA and IBM and all of the different vendors who are putting together these technological solutions to work with specific projects in the community to make the software be able to work and perform at its best with the hardware that only these vendors can even touch right now. So one of the biggest challenges that we have always faced in the HPC community is the legacy of code and trying to bring code that may have been around and evolving and morphing and being built on top of and patched and cobbled together and so forth for many, many years, decades even. The climate model being one that springs immediately to mind. there are a couple specific models within the overall CCSM platform that were originally written specifically for the SMP machines of the old SGI generation, where you didn't have to worry about running across a whole slew of nodes. Everything was a single big shared memory system. And so they were coded and designed with that in mind. And now the world has changed, but we still have that legacy of code. And DOE understands that the nature of that challenge, and industry understands the nature of that challenge. And I think for the first time, we're seeing a significant amount of financial and personnel resources on both sides being dedicated to helping the overall community bring as many of these different pieces of code as possible up to where they can be optimized to run on the IBM open power based system, as well as the Knights Landing and Knights Hill based systems, and the Intel Broadwell and Skylake commodity capacity type systems as well.
So if you don't mind me jumping in, I wanted to talk about the public-private question because it's a very interesting one, and it ties into something that Addison brought up earlier, which is risk, right? So the purpose of a public-private kind of going concern is around mitigating risk and potentially increasing innovation. And I think you've articulated very well the ways that we are working with vendors in terms of trying to solve those problems, creating architectural diversity so that the competitiveness of a couple of vendors we know really well, continues on, and there's not just one vendor, because that's beneficial to the whole ecosystem, the whole market ecosystem. But I think where we all share risk that I cannot figure out how to mitigate is workforce development. So we are in the process of, as I told you before, listening to users. And one of the things we keep hearing from everyone is we need to develop our workforce. And I believe that is a shared risk between our vendors and us. In some cases, we are competing with our vendors for the same people who will work at our place. And we need to figure out ways to get around that. There's a lot of smart people in the room here working really hard on lots of cool problems. So, how do we get together and create the commons that you have in this wonderful city, right, in this wonderful Bay Area, but somehow translate that so that across the ecosystem for HPC, we can solve the workforce development problem. It's huge, right? There's lots of interesting things to be done, lots of great science to be done, but not enough people working on it.
I completely agree with those points, and we have research that backs it up. If anyone wants to take a note really quick, there's a free download to a report we did for the United States Council on Competitiveness. You can find it on their website, which is www.compete.org, and under publications you look for the SOLVE report, SOLVE. It was all about the applicability of new generations of scalability up to Exascale for industry, essentially, although it's U.S. industry because it was the U.S. government paid for it. But if you're willing to extrapolate that industry in other countries might be the same, then go for it. But it focused on U.S. industry. I'm sorry, because that's where the funding was. But the idea, first of all, on workplace development is certainly in there. People can't find the bodies that they need, and I have some thoughts on that. But on the software side, this is where public-private partnership, could focus on some of the software, or I should say algorithms, techniques, programming models that are behind the application software, right? How do you get better mesh refinement, which would benefit all kinds of applications if you could do it? Can you solve what is this MPI plus X that we all keep talking about? In all of my years in this industry, out of all the terms I've ever heard, to me MPI plus X is the funniest, because all it means is we're going to take what we have today, that's MPI, we're going to add call it X, and then everything will be okay, right? We don't even know what that is. It is literally a code name for we don't know what we're going to do next.
Well,
right?
I would not. I don't think that's fully fair. We know what X is.
It's kind of fair.
Well, no. I mean, we know that whoever's API you're going to use, right, that is X, which is not why we don't know it. It's that we're giving people the option of choosing X.
It could be any API.
It could be one vendor's X or another vendor's X, but it's going to be X, and that's how you're going to be able to scale. And we know that.
MPI plus
pick
some
vendor
API.
Pick vendor API, and that is how it gets solved. And there'll be other things that, I mean, there's some other research. I mean, you're on the software side, right?
But it points out that it leads to the architectural diversity problem, which is that end users don't know what platforms they want to be on for Exascale right now. Do you want to be on GPU? Do you want to be on Xeon Phi, just Xeon? Do you want FPGAs? Do you want ARM? All right, and this is kind of a hard question right now.
So I would say that DOE is also very invested in portability, and we're pushing forward in terms of how, because we have two centers under sort of one facility. We think of Oak Ridge's leadership computing facility and our leadership computing facility to be two centers under one DOE facility. We're sharing a lot of crosstalk. You were talking about the NREs. There's a lot of crosstalk between those two spaces to try to make it so that you can have portable code. I know the vendors are kind of interested in that, because if they can make their code portable from one platform to the other, then the switching costs are lower, which means they can entice people into their space. So I think there's a little bit of motivation there. That's the extent at which I know your space. There are people from NVIDIA here and some people from Intel. But I would say that there's a lot of efforts in terms of portability. I think scientists are clued in on that as well. And so, back to you.
No, since we have just 1 more minute and we have like 15 more questions. There was one more
question. Go to
yes,
no.
One more question in the audience, right? You wanted to ask something, or? Yes.
Yeah, there's been a lot of talk about scalability, but virtually zero talk about utilization. And if you can build a smaller machine and get more utilization out of it, then why do we have to pay all the energy costs? So for the larger machine and get such poor utilization, one. Number two is that there is a lot of innovation in the labs, but the application folks, like you guys pointed out, are going to be conservative with respect to the algorithms that they've already built up, and there's an immediate economy there, right? The third part about this is that this is a zinger to Addison, was that you said
it's getting interesting.
You said that there's going to be a lot of crossover from the kind of workloads that you have, for the Googles, the Facebooks of the world. But if you really analyze those kind of applications, they tend, for the most part, not to be so interested in, they want to scale out to lots and lots of users running some kinds of database type of applications. Whereas in our multi-physics simulation world, we care, well, at least I care aggressively about the total time to solution, right? So that means getting as much deep utilization out of all the processing elements I have. And if you look at all the programming models, and you look at Linux, and you look at MPI, and you analyze it in a deep way, you see so much opportunities for performance that are going to, they're just that are basically being lost, not because you can't fix it. It's because the minute you fix it, you go back to the problem of, well, we want to be portable, and for one, so least common denominator. Number two is that if you start fixing this, you start getting to things that become completely divergent to programming models that these old, 30-year-old apps have been built on. So, it's like, do you think that really the total cost of ownership, which is really going to be power, we need a nuclear reactor charger Exascale system, right? Do you think that will finally be the reason why you'll for real do vertically integrated systems, as opposed to commodity and just throw it at bigger hardware, more power?
I'm parsing out the question. Do I think that total cost of ownership is going to be the reason for vertically integrated systems?
Well, let me tackle your first two questions first before
Yeah,
we hit that.
but please,
the third
please let's
one.
do it in one sentence each because everyone else is gonna live.
Your assumption for your first question, I think, is fundamentally flawed, because if you look at any of the large capability systems at any of the DOE labs, at least the unclassified systems that I'm aware of, utilization is, or lack of utilization is not a problem that any of them actually have. Those capability systems are some of the busiest. They're not underutilized in any way.
Per core, per register and cache, the bandwidth, all of the layers in the system, the hardware?
The entire system is occupied the vast majority of the time. Now, whether those individual pieces of code are utilizing every piece of every node every moment of the day, I don't have that level of visibility, but I know that the systems are being used to the maximum potential. Your second question had to do with
Transfer from hyperscale to HPC.
Was that your?
Technology transfer from hyperscale to HPC. He doesn't think it applies.
The workloads are so divergent, and if you start going more and more commodity, right, then it's actually a bad thing for multi-physics people, right? Because the problems that the commodity guys are solving.
I didn't say that hyperscale technologies would subsume all HPC technologies. I said that many of them would get adopted into HPC. Look at Hadoop. Look at OpenStack. It already happens.
I think there are a lot of opportunities, probably more. I just did a talk on this last week. It's kind of funny. There are a lot of opportunities for the HPC community to learn from and adopt specific technologies from hyperscale and the DevOps movement that we're not taking advantage of yet and really need to. But there will not be a point in time that I can foresee where the fundamental problem of a MapReduce type of system is equivalent to the fundamental problem of a tightly coupled parallel large-scale application system. Those two, as far as I can see into the future, will continue to be and need to be fundamentally different. Now, your third question.
Third question was, is total cost of ownership the reason why you'll see more vertically integrated systems, which assumes that we will see more vertically integrated systems, which I do think we will. I think you'll see a movement toward more application appliances. Not necessarily dominant, but you'll see more of them in the industry. I don't think total cost of ownership is the primary reason. I don't even necessarily think it's necessarily cheaper. I do think the primary reason will be reduced complexity, or hiding the complexity from the end user, from whatever the architecture is. That's going to be IBM's whole game, right? Is that you stop caring what the processing elements are in these systems. You care about the end-to-end workflow.
I think certainly I know of that there are some vendors who are doing more and more vertical solutions, particularly in the bio space. But personally, I think the smartest path forward and the greatest potential, and where we're going to start to see more vendors begin to play, is creating composable solutions. Not simply an entire end-to-end vertical, but composable pieces that can be combined together in a scalable manner to create multiple solutions.
I think at that point we're going to end more or less the panel. Just before, I think we want to start a new tradition that will ask each of you to try to guess in 2 words which country is going to build the first exaflop system and when. And the first panelists are going to guess it, and we'll have it in multiple conferences. We'll get from the HPC Advisory Council 100 teraflop of a supercomputers in the exascale time that he probably can put in his pocket. Addison, you want to start? Country and a year?
I'm already on record and haven't changed my answer. Japan. LinPack 2019, real applications 2020.
Okay. Everything is recorded here, so we have it evidence. DK?
I think I'll go for US. I think
Year?
it will be around, again, 2022 or something like that.
Okay.
Let's see.
I'm going to say US, Livermore, 2021.
Wow.
Okay.
You guys don't think Japan can get there?
Specific, do you want to name the machine?
So
I'll name it Bob.
wow. So you have a smiley face too?
Yes.
Awesome. So for me, whenever I think of Exascale, I don't think about LinPack. It's not a very interesting game. Sure, you get to say the number, but I think in terms of the first Exascale app or the Exaflop app that really grabs the mind, I would say 2024 and United States.
Okay. With that, I want to thank you, Addison, DK, Mike, and Richard. Thank you very much.